I now call to order the Society's 2,453rd meeting in the 150th year since its founding on March 13th, 1871. Good evening, everyone. My name is Larry Milstein. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends to tonight's lecture by Roberto Tamai. And a special welcome to a few PSW members and member speakers, Dick Garwin, Wendy Friedman, Carrie Liss, and John Grunsfeld. Welcome. Tonight's meeting is being held via Zoom so that our speaker, Roberto Tamai, can join us from his location in Germany. As of now, we're planning to have the next meeting in person, but this will depend on COVID and on the measures instituted by government authorities and the Cosmos Club. The venues will be posted to the website and highlighted in the announcements that will be sent before the lecture. Please check the website frequently for updates. All in-person meetings will adhere to the COVID-related rules of the District of Columbia and the Cosmos Club. Proof of vaccination, including a picture ID, will be required for in-person attendance. As of now, masking is required, and we suggest getting tested for COVID infection within 48 hours of the event. These requirements are subject to change with changes in the COVID-related rules of the District of Columbia and the Cosmos Club. Please check the PSW website often for up-to-date information. Of course, we will be live streaming all meetings to YouTube for our remote audiences to enjoy and to ask questions in the YouTube chat box. And final versions of the live stream recordings will be posted to the PSW website, PSW YouTube, and Vimeo channels, where they will be permanently available for everyone to view without charge. The Society is grateful to the sponsors of the 2021-2022 lecture series for their support. The Policy Studies Organization, in cooperation with the American Public University, and a generous sponsor who's asked to remain anonymous. We also like to recognize PSO and APU for supporting the reprinting of all of the bulletins of the PSW 1 through 16, which are available on the website in PDF form for free and can also be purchased on the web from Amazon. I'm pleased to announce the following new members have been elected. Matthew Kaywood, CEO of Action Figure, a transportation information software company interested in the environment, evolution, neuroscience, astronomy, AI, and applied mathematics, who learned about PSW by attending an event. Matthew also has been a dealer in rare scientific and medical books. Janice Soreth, a physician, interested in many areas of science, including physics and astronomy, chemistry, anthropology, who learned of PSW from PSW members, including Carl Merrill and Lloyd Mitchell. Julie Miller, General Counsel at AHIP, interested in ocean and freshwater biology, astronomy and space science, and public health and policy, who learned of PSW through announcements of PSW lectures. Dan Sisson, Assistant U.S. Attorney in the Attorney General's Office of the District of Columbia, interested in computers and astrophysics, who learned of PSW from his father-in-law, Gordon Martin. And tonight's speaker, Roberto Tamai, whose interests will be clear in a small part from tonight's proceedings. We welcome them all to membership. If you're not a member and would like to join PSW or support the Society, you can do so through the PSW website using the blue Join button on the upper right-hand corner of the home page. We welcome new members and appreciate donations. Recording Secretary James Hewlin will now read the minutes of the 2442nd meeting and the lecture by Olivier Goyon on extreme adaptive optics. James, the screen is yours.
Good evening, everyone. On January 14th, 2022, by Zoom webinar broadcast on the PSW Science YouTube channel, President Larry Milstein called the 2452nd meeting of the Society to order at 8:02 p.m. Eastern Standard Time. He welcomed new members, and the recording secretary read the minutes of the previous meeting. President Milstein then introduced the speaker for the evening, Olivier Goyon, professor of astronomy and astronomer at the Stewart Observatory at the University of Arizona. His lecture was titled Extreme Adaptive Optics, the Technology Behind High Contrast Imaging of Exoplanets. Goyon began by summarizing his October 8th, 2021 presentation to the Society. In that first lecture, Goyon introduced the concept of adaptive optics, which minimize atmospheric blur from ground-based telescopes. The technique requires three main components: shape-changing mirrors, one or more waveform sensors, and a computer control system that processes the sensor data in real time to compute the necessary corrective mirror movements. While there are many types of adaptive optics systems, they can generally be defined by two values: field of view and wavefront error. Extreme adaptive optics, or extreme AO, systems are optimized to deliver the best performance over a small field of view to image faint exoplanets orbiting close to other stars. The higher quality image of an exoplanet, the better able scientists are to study their spectrum for signs of habitable environments. Imaging exoplanets requires three techniques to be combined: extreme AO to correct atmospheric turbulence, a coronagraph to mask the light of bright stars, and smart image processing to recognize planets. The instrument Goyon uses for his research is the Subaru telescope in Hawaii, for which the instrument team is developing extreme AO techniques. He showed many images of the telescope and gave viewers a tour of its extreme AO instruments. The Subaru coronagraphic extreme adaptive optics looks like a large black box. Inside are a complicated array comprising two layers of adaptive optics, including the multitude of cameras and optical sensors required to obtain the data necessary to compute quality mirror corrections to remove atmospheric blur. Goyon showed detailed diagrams and explained the instrument's internal functions performed by the visible bench and the infrared bench. The telescope compresses its 8-meter beam into approximately 1 centimeter and feeds it to equipment including 11 total wavefront sensors and a deformable mirror 20 millimeters in diameter, with 2,000 independent actuators operating at approximately 10 kilohertz speed. The speaker then discussed in detail the telescope software and the algorithms that power its adaptive optics control. In summary, the input comes from the waveform sensors, which tell the software what atmospheric optical aberrations have been imprinted on the optical beam. This data is collected from cameras taking images between 2,000 and 4,000 times per second. The software feeds that data into a control matrix to derive a control signal output, which is then sent to the deformable mirror. Extreme AO are unique because they require a very high-speed processing, a large number of control modes, and high accuracy and precision to exquisitely correct constantly changing distortions. To obtain those measurements, extreme AO optimizes the wavelengths it measures to the stars being observed and uses a pyramid waveform sensor to aim the telescope. Goyon then discussed advanced control techniques for extreme AO. Conventional AO takes the last measurement of a waveform sensor and multiplies it by a matrix and sends an output to the deformable mirror. Advanced AO control will use multiple past measurements from multiple sensors for predictive control. This advanced technique is so complex that machine learning will be required for the technique to become practical. Goyon then showed examples of how advanced AO control can learn and improve image resolution. Advanced AO control may also use the focal plane image as a source of information to improve waveform measurement. Goyon's team is developing a technique to look at an image of an obstructed star to control for the speckles of light created by the obstruction. The speaker's final slides presented the Subaru Glint module, which uses interferometric waveform sensors to measure starlight. Goyon then concluded and answered questions from the online viewing audience. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. President Milstein adjourned the meeting at 9:31 p.m. The temperature in Washington, D.C., 8 degrees Celsius. The weather, partly cloudy. And the number of concurrent viewers of the Zoom and YouTube live stream, 63. And views on the PSW Science YouTube and Vimeo channels in the first 2 weeks of the lecture, 291. Respectfully submitted, James Heelan, Recording Secretary.
Bravo, James. Thank you very much. That was an excellent summary of the lecture. If anyone has comments on the minutes, please send them to Recording Secretary Robin Taylor at correspondingsec@pswscience.org. The minutes will be posted to the website in due course, corrected or revised as advisable in light of any comments that are submitted. We now turn to tonight's lecture on the European Extremely Large Telescope, the largest terrestrial visible light telescope in the world currently under construction. Our speaker, Roberto Tamai, is the program manager for this project, formally known as the European Southern Observatory's Extremely Large Telescope Project, that is ESO's ELT. Before taking on the role of project manager for this massive and hyper-complex project, Roberto was director of engineering at the European Southern Observatory. And before that, he served as head of the technology division at ESO. Among other engagements in his long and distinguished career at ESO, Roberto served as project engineer on the ESA Hypersonic Plasma Wind Tunnel project at the Italian Aerospace Research Center, as a mechanical engineer at ESO's Paranal Observatory, and as head of engineering and then deputy director of ESO's La Silla Paranal Observatory. Roberto was educated at Naples University, Federico II, and then at the University of California, Berkeley. All questions will be fielded during the Q&A session after the lecture. Roberto, the screen is yours.
Good evening, everybody, and thank you for giving me this great opportunity to illustrate the progress of the construction of the biggest ground-based visible and infrared telescope in the world. This evening, we have with us also in the background my client, the program scientist Michele Cirasuolo, who will accompany me in the illustration and progress and the capability, scientific capability of the telescope. Thank you, Michele, for being with us. Okay, so let's start briefly with what is ESO. ESO is the European Southern Observatory. It is an intergovernmental treaty organization that was founded in 1962. The headquarters is in Germany, here close to Munich. We operate telescope only in Chile. We have 750 staff. Half of them, more or less, are here in the headquarters in Munich. The others are in Chile, operating the various sites. What is the mission? We build and operate the world-class ground-based astronomical facility, but we also promote collaboration in astronomy. Today, there are 16 European member states. We do have a strategic partner, Australia, and host and partner is Chile. Briefly, in one slide, what are the goals and the programs? We have the La Silla Paranal Observatory that is in operation in Chile. These host La Silla telescopes and VLT and VLTI at Paranal. So these are two sites, part of the same observatory. That also include APEX, that is a partnership with the Max Planck OSO and ESO that will finish this year. Another site is ALMA, that is in operation. This is a partnership with NSF and NINS, Japan. We do have the ELT that is under construction, that is the core of this presentation tonight. We also have the CTA South that is in preparation. I will briefly illustrate what is that one. Plus, there are many organizational activities in support of the mission, such as we develop new technology, we do research and development. We also do science and engineering research, training of students, fellows. There is a big outreach program as well that is part of the organization. So let's start where everything started, at La Silla, that is located in the southern part of the Chilean Atacama Desert, that is around 600 kilometers north of the capital of Chile, Santiago, at an altitude of 2,400 meters above sea. It is located far from all the light pollution sources and has one of the darkest night skies on the Earth. La Silla has been the ESO stronghold since the 1960s, and here ESO operates two of the most productive 4-meter class telescopes in the world. We do have the so-called New Technology Telescope, is a 3.58 meter main mirror that broke new ground for telescope engineering and design. In fact, it was the first in the world to have a computer-controlled main mirror with active optics technique. That is a technology developed at ESO and is now applied to most of the world's current large telescope. The second one is the first that was built there, is the ESO 3.6 meter. That today is the home of the world foremost extrasolar planet hunter, HARPS. That's the name of this instrument. That is a high accuracy radial velocity planet searcher, a spectrograph with unrevealed precision. It has been here that the observation has been made to discover the planets around Proxima Centauri, that is our closest star. That is an amazing discovery announced last year and another one also recently. The infrastructure at La Silla also hosts many other smaller telescopes. These are made by many ESO member states for smaller specialized projects. In addition, we have the two, in addition of these two, there are 11 other smaller telescopes there. We then go to Paranal. Here it is. This is the top of the mountain that hosts 4 8-meter class telescopes, UT1, also called ANTU, UT2, that is Cuyen, number 3 Melipal, and number 4 Yepun. These are the names chosen by local people in Chile that, if I remember correctly, they mean the sun, the moon, then we do have the South Cross. So these have been chosen by the locals in order to identify this the biggest telescope that we have over there. We then have a VST, that is a visible survey telescope, and we do have a VISTA, that is an infrared survey telescope. We also host up there 4 additional auxiliary telescopes, all of these to create the BLTI, the interferometric array, that can also work as individual units. And also the 4 UT could be put together for an interferometric technique. So what ESO does, ESO builds the telescope and all the infrastructure. The telescope is the funnel of the photons that are there. All of this is directed towards the instruments. That is where the light is analyzed. The instruments are developed in a partnership with consortia. Consortia are based by institution, university, and more. So ESO provides the capital cost. We do oversight, support them. We also provide the critical items to the instrument consortia. And the effort from the institution, part of the consortia, is compensated by means of guaranteed time of observation on the ESO telescope. We do operate the entire facility. It is ourselves, it is me, our colleagues, Michele, and more. We do operate and maintain the telescope at the observatory with an average technical downtime that is less of the 3%. ESO, as said at the beginning, is also part of ALMA, that is the largest sub-millimeter radio interferometer in the world. It is in operation since 2011. This is a global partnership together with NSF, the National Science Foundation, and NINS, the National Institutes of Natural Science, a Japanese research institute corporation. We do also have a cooperation with the Republic of Chile. What is ALMA? It is an array in operation at 5,050 meters above sea level in China Tour Plateau. It consists of 66 movable antennae of 12-meter diameter over a 16 kilometers plateau. It also includes backend and correlator, and the operation support facility, that is where we do maintenance and we operate the site. We do maintenance of the antenna that are driven down in order to do maintenance on them, is at 3,000 meters above sea level, and it is near San Pedro de Atacama. We do have also the Cherenkov Telescope Array South, a CTA, that is going to be hosted and operated by ESO in the Paranal Armazones area. What is this? You know that the gamma rays that are generated by stellar explosions or by the jet discharged by supermassive black holes interact with the Earth atmosphere, producing a cascade of high-energy subatomic particles that in the air moves faster than the light. And they create a sort of shock wave in front of them. But this time, this is a photonic wave of a spectacular blue lights that is called the Cherenkov light. So what we do, the collection of these flashes that has a duration only of a billionth of a second duration, and their reconstruction gives important information about the source of the original gamma ray. So what we are part of that at 8% of this CTA observatory. It offers important operational and scientific synergy with us. The infrastructure started last year, and this will, the effective construction may formally start this year. Now, all of this infrastructure, what do we do? These, on top of obtaining all this scientific information, they have allowed also to win Nobel Prize, for example, in 2019, for the discovery of an exoplanet orbiting a solar type star. This was won by Didier Queloz and Michel Mayor. This was allowed to discover this moving of an exoplanet around our closest star, Alpha Centauri, Proxima Centauri. What we see here is Proxima B, this one that is moving. It is a planet with a mass comparable to that of the Earth that is orbiting the star every 11 days and is within the habitable zone of this star that you see here covered in order to avoid to be glanced by that. So it is a star at a distance similar to that between Sun and Saturn at approximately 1.3 billion kilometers from us, meaning it is the most closely orbiting exoplanet ever to have been directly imaged. So our facility has helped the scientists in the identification and discovery of this exoplanet. Then we had in 2020 the Nobel Prize that was won by Reinhard Genzel and Andrea Ghez for the discovery of a supermassive compact object at the center of our galaxy. I'm sure you have seen in the news that the black hole identified at the center of our galaxy, and now they did measuring the orbit of the star around our center of galaxy, the black hole. That is the only currently known explanation of the trajectory and speed of this scientific object around this position. But all of this is thanks to the, let's go forward to the future, the potential of the EELT. This is a field of view and how it is seen by the Hubble Space Telescope, well above our atmosphere and therefore undisturbed by the Earth atmosphere. And this is the sharp image that we can obtain with the ELT. That is, will be 15 times as sharper than Hubble Space Telescope. So all of this is an image that can obtain without the application of the various techniques that the ELT will have. And this is what we will be capable of achieving in terms of resolution and capability, where every single disturbance that the telescope or the optics might introduce will count in impacting these fantastic images that we will see. But now let's go into the situation of the ELT. What is the ELT and where we are with its construction? First of all, I strongly encourage you to go and visit our recently created web pages, elt.eso.org, that it gives at first an overview of the telescope, of the dome, of the main structure. Then we go more in details about the optics, the optomechanics component of the telescope. We illustrate the instruments that are part of the program and demonstrate what are today the scientific goals of the facility. What is that? It is a 39.3 meter primary mirror that includes adaptive optics. The construction started in 2014, planned to be completed in 2027, the first part of the program, because then there will be a continuous development of new instruments that are part of the ESO program. The budget and the cost today is around 1,300 million euro. The first science light is today planned for the end of 2027, where on Cerro Armazones, that is in the second region of Chile, in the north, and these will be operated as part of the La Silla Paranal Observatory. Why are we in Chile? Here, this is an image from the International Space Station. You see here, north to the south of Chile. And you see that Chile, we are located, ALMA is here, Paranal, VLT, Armazones are located in this area. And you see that this is always above the clouds. So these are the clouds, and there is an inversion layer meteorological effect that is keeping the clouds down. And we, in our location here, are most of the time, really, 99% of the time, above the clouds. We are in the Atacama Desert that is extremely dry, 90% clean sky nights with low turbulence, very limited light pollution. The closest town is 120 kilometers away. There is obviously an excellent vision of the southern hemisphere. And here you see a comparison of how at naked eye you see a poor sight, therefore this wrinkling of the star, and how you see it at naked eye in Chile. Where are we? Here is the area. This is a picture taken by an airplane, normal airplane. Down here you see Yuyayaco, that is at more than 200 kilometer distance from Paranal. And you see how clear is the sky here. This is Paranal Observatory, and here you see the 4-unit telescope on top of that one. And Cerro Armazones is here at 25 kilometers distance, and this is where we are building the ELT, Cerro Armazones. From this picture, you do not see already created access road, and there is also electrical grid that you have brought in. So this picture is well before we started the construction of the ELT. It is Cerro Armazones at an altitude of 3,046 meters above sea level. There are around 330 clear night sky per year. It's a very stable atmospheric condition. There are rare rains, but they occur. Little snow, but very strong wind. It's dry again, high UV radiation, and unfortunately, it's a very high seismic area. But why we go for increasing the size of the telescope? In this picture, you see the comparison. Here are the 4 UT of Paranal, and this is the diameter of the ELT, of the ESO extremely large telescope. And here is a comparison with many other well-famous telescope. And here you have also a tennis court and basketball, just to give you a feeling of the size of that. Of course, bigger the better in terms of collecting area. You should see the telescope as a funnel of photons, and therefore bigger the funnel, more photons you get, meaning you can detect fainter object, fainter meaning far away. So more photons are brought to the focus of the telescope and we can observe fainter star. But also we increase the spatial resolution, capability of distinguishing 2 objects close to each other. But on the ground, all of these requires adaptive optics. Adaptive optics is required in order to remove all the disturbances that are introduced by our atmosphere. So some of the scientific goal of the ESO ELT, we start with the exoplanet, and therefore all the well-known questions that today we cannot yet answer: how the planet system forms, how common are the systems like our solar system, which atmosphere do the planets, the exoplanet that we identified so far have. Today, this is something that we do not have the tools to understand how the atmosphere of the exoplanet is. Are there other Earths? And if we can detect signs of life, this is for the exoplanet. Then we have the Galactic Center, and therefore testing the validity of the general relativity around the supermassive black hole. And this is something that the ELT will help in answering. Resolving star populations, what is the evolution, merger history of our Milky Way. Then we have questions related to the large redshift universe. Are we expanding? What is the acceleration, confirmation of all of that one? Did they reionize the universe when this happened? Then we have also cosmology and fundamental physics. So what is the nature of the dark matter? Can we measure the fluctuation of the universe expansion? This is very important and interesting questions that we would like to give confirmation. And are fundamental constants truly constant? Let me anticipate. I'm leaving the astronomy world, but by education and my work, I am an engineer. So that's why I'm also together with the client that has placed with all his team all the questions and working for that one. But this is something that really is, for me, the opening towards the unknown, because when you have such a powerful facility, it will certainly open windows to the unknown, and therefore we will be asking ourselves new questions that today we don't yet know, because the facility will open windows and will give us the vision and the understanding of things that today we do not imagine, and therefore opening all of this unknown world that will certainly occur, that has certainly occurred every time that we have a new facility bringing us forward. So as I said, one of the top goals of the ESO ELT is to find and characterize exoplanet. This is going to be the first one to explore Earth twins. So there are today over 500 planets that are known today. And here you see this is the sun. And in the blue flow, that is the habitable flow, you see here we have the Earth. Here, there is another comparison with another star. This is Gliese 581, that is around 20 light years away from us. And here you see the other exoplanet that they've been identifying, turning around this other star that have been discovered, and some of them are in a habitable zone. So with this telescope, we will be capable of performing spectroscopy of the atmosphere of this exoplanet and identify if there are biomarkers, and therefore water, oxygen, ozone, all what we know are needed in order to have life on the planet. And with this, we will be capable of not only direct imaging this exoplanet, but also performing spectroscopy of their atmosphere to identify if there are any biomarkers over there. This is an artist rendering showing what will be the final situation on the top of Cerro Armazones. But you should notice here the people, a car, this is a van, and therefore just to give you an idea of the size of that. The platform here will host the chillers, heat exchanger, and these are downwind that is coming here in order also to reduce as much as possible the heating disturbances potentially generated to the image. And here is just to give you a feeling of the size and putting it into perspective. That's the White House, and if I put the telescope in front of that, that is going to be the size of the telescope. How does it work? Mechanically, we do have, this is an alt-azimuth, altitude-azimuth mount that the structure points and tracks to compensate for the target motion and therefore to compensate for the Earth rotation. The main structure, the telescope, holds the optomechanical units, but each optomechanical units can realign the optics that it hosts on the telescope. This because as stiff as you can construct the main structure, there will always be bending and deformation that are too big for the precision required by the telescope. And therefore, we have to constantly realign the optics in position. And this is done by means of the optomechanical units to compensate also for external perturbation. Finally, the lights is directed here on the focus, where there are the instruments that will analyze the collected lights and perform imaging, spectroscopy, and more. All of this fighting against the gravity, wind, thermal deformation, atmospheric turbulence, and obviously all the earthquakes. What is the light path? Here is collector, the main primary mirror that reflects the lights to the secondary at 60 meters high, reflected back to the tertiary mirror that is at the same height of the primary, to the fourth mirror, the fifth, and finally going down here. And I will explain the reason of all of these ping pong of the lights inside the telescope that is mostly in order to clear the lights from various disturbances. Is an innovative 5-mirror anastigmatic optical design that incorporates an adaptive optic deformable mirror, M4, that is located at the intermediate focus. The light passes through the M4 and of that one to then go to the instruments. So you see that you have seen that the primary 39 mirror, that is the bigger funnel of photons, that is then reflecting. These are powered mirrors, so they can be positioned, controlling their shape and in their position. To then, there are finally the 2 flat mirrors, M4 and M5, to redirect the focal plane to the instrument signs here. The primary is composed by 798 near hexagonal segments that have to be realigned at the nanometers precision in real time. They are composed of 6 petals, each of them made of 133 different segments. So we have to fight against all of that one in order to reach the smallest fraction of the wavelength at nanometers level to preserve all of that within 1 arc second. What is the 5-mirror anastigmatic concept, and why do we have that one? First of all, in order to limit the size of the dome. Bigger the dome, higher the cost, while with this 5-meter compact design, we have a compact optical design with a short M1 focal ratio, meaning high sensitivity to the mirror misalignment. But the overall size, in fact, implies high wind cross-section, and therefore the telescope and the M1, and low structural stiffness. So what we've given is a fast integrated waveform control that is there in order to compensate for the errors introduced by the telescope. We also took into account what are the construction limitations, for example, the size of the M2 that has to be up here, that is a 4.2 meters, that was too large to have it deformable up there. And that's why we have introduced a deformable mirror down at an intermediate pupil created that has been by a powered M3. And that's the M4, that is a 2.4 meter, 1.8 millimeter thin. This has a multi-stage wavefront control strategy. So what we have offload drift from fast and low stroke subunits to slow and high stroke them. We have the tracking by means of M4 to M5 and then to the telescope, a sort of procedure to have the tracking of the telescope of the scientific object. And we also have an additional post-focal adaptive optics that is located in the instruments. So we do have adaptive optics in the telescope for certain altitude from ground, and then we can introduce additional post-focal adaptive optics inside the instruments themselves. We do have a diffraction limit that is applied to all the wavelengths in a 10 arc-minute total field of view. So we do have the built-in atmospheric turbulence rejection in the K band with a single conjugate adaptive optics plus the ground layer adaptive optics. Few more details and then we see what is the status of the construction. We have spoken about the M1, is a 39-meter concave aspheric segmented with active and segmented shape control. The secondary 4-meter convex aspheric. This is a passive. We have avoided to have heating up here, but there is a position control of the mirror. The tertiary down here is a 4-meter classical concave aspheric mirror. This is also an active plus, this is active mirror plus position control. Active meaning that we can change a bit the shape of the mirror itself by means of the actuators underneath the mirror. The quaternary is a 2.4 meter flat. As said before, is a 1.9 millimeter thin. It is segmented, so it's made up of 6 petals, and it is adaptive plus the position control. The last mirror before going to the azimuth focus is a flat mirror M5, elliptical, 2.7 by 2.3 meter, passive, but with fast tip tilt. Part of the optomechanics, there are also the laser guide stars that are there in order to create an artificial star for the adaptive optics, where the natural star is not in the field of view of the scientific field of view. Last, we do have the first set of instruments. We do have Mikado here, that is the adaptive optic imaging camera for the ESO EELT. We have Harmony, the integral field spectrograph that is operating over a large wavelength range from V to K. And last is METIS, the infrared imager and spectrograph of the EELT. We also have Maori, that is the adaptive optic to feed Mikado. In this image, I'm also reporting the prefocal station here. That is the tool that will redirect light to one or the other instruments during the observation. In this image, we have placed all of the instruments on the same platform. Just to give you an idea, this was the original plan. Today, we are exploring, and most probably some of the instruments will start to be mounted on the opposite azimuth platform in order to give flexibility to the program. So where are we? And with the construction now, all of what you have seen is part of the engineering, is part of the previous phase. Now we are building that. So in place today, these are all the contracts. I'm sure it is difficult, but maybe you can read it afterwards in details. These are all the contracts that we have in place and that are up and running today. And I want to give you a feeling of where we are with the progress. This is the column that is indicating the design. So in green, we are at 95, 100% level. So most of them have completed the final design, and they are in the construction, in the manufacturing. And here you see with the color, again, to give you a feeling, we have in orange a status between 50 and 95%, and in red, less than 50% progress. And finally, in the integration part, some of them have even completed the part of the integration on some other subsystem. Many contracts have completed. So there is a very good progress with most of them. Today we have 37 running contracts, above 500,000. So these are only the main contracts that are part of the program, including the 4 instrument agreements. We do have already 11 contracts that are either closed or are in a warranty period. And now, this is the final design of the dome. Inside here, obviously, there is the telescope. This is the final design of the main structure, of the main telescope structure. But let's go further in details. The dome and main structure is a single contract that we have signed in 2016 with a consortium of Italian company Astaldi and Cimolai. The design activities are going on and are now completed in Europe with the preliminary design review of the dome in 2017 and the main structure preliminary design review in 2019. Now we have also already successfully passed the final design of both the dome and the telescope recently in September last year. But part of the design, these included also prototypes, qualification activities and models. In fact, here you see one of the louvers, here you see one of the boogie trolley of the dome. This is qualification of the installation of the cladding and more. Where we are here, this is the site, is managed by the consortium. We had the first stone in 2017. Today it is planned to be completed by the end of 2025. So here you see the top of the mountain that has been flattened. We are at 3,046 meter altitude. That is the access road. The site, unfortunately, was closed for 1 year, from June to May last year due to COVID. It has resumed now in May last year. Today there are something like 140 people on site. There is also there a COVID limitation in order to avoid more than one person in the same room. The dome pier has started, but also the telescope pier. You will see some picture afterwards. There are already more than 200 ESO containers that have been delivered to the site. We have sent, the company, the contractor has sent many structural elements. The seismic isolated of the auxiliary building all around the dome. You've seen that there is an auxiliary building that also that has been installed on dampers to avoid transmission of earthquake to the building. And here, just to give you an idea, here we are underneath the auxiliary building floor, and you see here that is placed over these seismic dampers. The dome steel structure, we are speaking about more than 5,000 tons, 100% has been manufactured, half of them has been shipped to Chile. These are the dome trolley that you've seen before. Each of them weighs more than 27 tons. All of them are produced. Half of them have been delivered to the site. You see here at the base camp of Cerro Armazones. This is the rail of the dome, and here are the windscreen that is progressing in the construction. All of this is already on site, and you see here the delivery of the pieces. That's one of the main area of the storage. This is the interface. We are speaking about 12 meters, 3 meters diameter. There is the installation of the crane in the center of the telescope and of the dome for the construction. Here is me in the center of the dome, in the center of the main structure foundation, 3 meters thin. And these are all the walls that are being erected around to host then the dome. For me, the feeling, I was there last week after more than 1.5 years that we couldn't go there. It's like entering the Colosseum. It's gigantic, it's fantastic. It's also scaring for the size of view. But you see here all the progress. They are now progressing both on the walls of the dome here and also the foundation of the main structure. They have many pieces there. What you see here is the crane that has been delivered. It's a more than 1,000 crane capability that is down there that will be used on top once the foundation of the dome is completed. There is progress on the various subsystems. Here are the isolation and locking system to avoid transmission of vibration to the dome, to the telescope. There is excellent progress of the azimuth tracks. Cutting and welding is completed, all of them. They are progressing with the machining and painting. All the hydro-bearing system of the telescope has to be tested and validated before being shipped to Chile, obviously. Here you see all the serious production of the vertical seismic isolation. Here you see underneath the main structure. And this is a locking system that will have the function of a fuse that will break in case of a bigger earthquake in order to avoid that further damages to the telescope. And that's the situation and the progress of the dome and main structure. Moving on with the primary, with the various optics. This is one of the 798 segments, how it is constituted. There are several parts. We have the blank up here that is made of Zero-Dur. Is a glass ceramic material built by Schott. We do have the edge sensors here to read the relative position of each segment with respect to each other. The segment support here is to distribute the weight over 27 axial pad in order to avoid imprinting from one of them, so uniform distribution. We have the fixed frame that is one of the interface to the main structure. And then we have the positioning actuator, that are the actuators to put in place each segment with respect to each other. So you see there are thousands of component building. This is one of them, but each of them, part of the main mirror, is composed by all of these items. And all of these items is one of the contracts that I was mentioning before. Where are we then? The blanks are produced by Schott, Germany. I was mentioning these glass ceramic materials, Zero-Dur. They start to be circular or 1,520 millimeters each, 5 centimeters thick. They are machined, acid etched by all surfaces except for the optical surfaces that will then be polished. We are in a full construction. Something like already 50% of the total number have been already produced and delivered to the polisher. And here you see the segment support. Also, the design was completed by TNO in the Netherlands, and now they are manufactured by VDL by means of a build-to-print contract for their serial production. As mentioned before, this is a 27 points Wiffle-3 support. What you see here is the fixed frame. They are upside down. So the black part that you see here is the dummy, simulating the blank here. And this is used for their transportation, but also for the final installation on the telescope. And also for them, both the fixed frame are all produced. You see they are here in box. We are pretty close to ship them to Chile. And also the segment support, we are at the level of 30% of the total serial production that has been done. And here they are. This is the warehouse of the polisher, Safran Reos, that is receiving the blanks that are here in these brown boxes and the segment support that are produced by VDL here in the white boxes. So we have already delivered several hundreds of both of them. And Safran Reos has recently started the polishing, the manufacturing of them. These include the pads bonding, grinding, polishing, and this is the process that will be done here at Safran Reos in Poitiers, include the hex cutting, so from circular to the hexagonal shape, ion beam figuring, final polishing, and obviously all the testing. There are in total 13 processes, all of them have been validated, and very recently there are finally the first 31 segments that are in production. And here's some picture. Here is how we deliver the blanks, the brown boxes that I was showing before contain each of them 6 blanks. And here is how we deliver the segment support to the polisher. And here's some picture. Safran Reelsk had to rebuild an entire building of more than 5,000 square meters in all the processes that are needed to bring the blank to the final shape that you see here with one of the first fringes that they have obtained. So all the processes are now validated and they are finally in production. We then need 2 more contracts to complete the M1 that I mentioned before. One is the positioning actuator. These are developed by Physik Instrumente, a German company. They have a stroke of ±5 millimeter with a tracking error of 2 nanometer. Incredible, with absolute accuracy of 5 micron. These are 2 stages, motor spindle plus the piezo actuator. There has been an intensive testing of them. Obviously, also in the climate chamber, simulating the final environmental condition at Amazonas, plus gravity test rig. These have been also tested at ESO here in the headquarters for several working conditions. In total, PI has to produce 2,500 of them, plus 800 control electronics. We have already received the first series of 177 of them, so now we are in the serial production. The last contract part of the M1 units are the edge sensors that you see here. These have been developed by a consortium of Fogal and Micro Epsilon. Fogal is a French company, Micro Epsilon is a German company. They have a low noise inductive sensor plus the electronics. They measure piston plus gap and shear between the various segments. Also here, the technical specs are incredible. They have a range of ±0.2 millimeters with a resolution less than 1 nanometer with a repeatability of 10 nanometers. So with these sensors, you can measure the speed of growth of the grass in your garden. There has been an intensive design and qualification phase that is now completed. In total, the contractor has to deliver more than 4,500 heads plus 800 reading electronics. And also here, they are in the serial production. They have delivered the first series batch. And you see here some picture of them in the climatic chamber of the electronics and more. We then move on from M1. We go to the following mirror, M2 and M3. There is a big synergies between M2 and M3. The M2 is a passive 4-meter convex mirror, highly aspheric, incredible mirror. You will see some picture afterwards. The M3 is an active 4-meter concave, so more classical, milled aspheric. They have the same sides, same kind of support, mass and stiffness, shaping system, positioning, all of them is pretty similar. So we have one single contractor for the 2 cells and the manufacturer that is Sener, sorry, here there is a typo, Sener in Spain. There are 2 polishing contracts with Safran Reelsk, and there is also an optional test that we have to put together the mirror in the cell before the delivery to Chile, and we will do that at Safran Reelsk. So where are we with the construction? The mirror is fabricated and completed. Also, the mirror is done of Zero Dur and has been received in 2019 from SHOT. The M2 is well progressing. Is the world's largest convex mirror ever built, highly aspheric. There is a challenging testing with difficult aspheric reference optics and stitching method. We have the contractor is reusing the tower, the metrology tower that was used for the primary mirror of the VLT is now going to be used for the M2 and M3 polishing. The pads has been completed, the installation of them, and we are at the pre-polishing well advanced for the M2. We are at 2 micron surface error. The M2 cell is developed by Sener, and you see here the M2 cell, and this is where we are with the M3. So the M2 is very well manufacturing, and it's already progressing with the assembling, integration, and testing of that. And here you see a fantastic picture of the secondary mirror. We are still in the pre-polishing phase, but it starts to look like a mirror indeed. The M4 unit is also well progressing. This is where we host the adaptive optic mirror. It's a 2.4 meter made of 6 sectors. And you see here one of them is I repeat, 1.9 millimeter thin. Here we have already, the contractor has already installed all the pads and the radial membranes. These we have already delivered all the 6 of them to complete the first M4. And we, because of the fragility of the item, we have in the plan also, and we have already delivered the 2 spare shells for the second spare M4. These will have more than 5,000 voice call actuators plus capacitive sensors with high bandwidth control at 1 kilohertz. So you see here the shell. These are the bricks that have all the actuators in the back that will be positioned in the reference body. Silicon carbide item, pretty complex to manufacture. We are at the last phase of lapping this surface that is the reference for all of these actuators that will shake the mirror to remove the atmospheric turbulence. Last but not least, we have the M5 mirror, part of the telescope. The M5 mirror is a 2.7 by 2.3 meter flat. Also these, and you see here the petals, each petals has to be CVD coated in order to reach the flatness and the roughness needed by our wavelength. All of them, they have to be brazed and polished. And this has never been done in such a size. So this is one of the highest risk of the program to finally have achieved this that you see here in their artist rendering. Today, we are ready for the brazing before the delivering of the REOSC for the polishing. The M5 cell is developed by Sener. It has a custom designed piezo actuator for the fast tip tilt stabilization of the mirror. We have at the final design and qualification that is almost completed and is planned for the first quarter of this year. Then we have the pre-focal station. You remember I've shown this in one of the pictures. This is the tool that will redirect the beam towards one or another instruments. This is developed by IDOM, a Spanish company. This controls and redirects the telescope beam to the various forces. It hosts the natural guide star wavefront sensing for the telescope control in order to track beam acquisition and guiding. There is also mirror positioning shape control. This tool also hosts, somebody call it a test camera, we call it the phasing and diagnostic station, that it is here, that it will be located in this position. That has the M1 segment phasing sensor to place all the M1 segment in phase from each other. It has the basic adaptive optics before they hand over to the instruments. It includes a camera and tools for the telescope alignment and commissioning. It will remain a stable reference during the future operation of the telescope. Where we are in the design phase for the pre-focal station, we are already in the manufacturing, while for the phasing and diagnostic station, we are in the final design situation. And pretty soon we will start the procurement of the long lead item. And here is an image just to give you the feeling. This is this part of the pre-focal station. This is a visit that my colleagues that are following up the contract with Odom did last week. For the adaptive optics, we have the system that will include the 6 of them. The entire system is composed by the laser source produced by Optical, German company, by the laser projection subunit. Here is a telescope to launch the laser to the sky. This is produced by TNO, a Netherlands company. We are in the final design that is happening in these days. Then we do need the special heat exchanger that are developed by Teco Electra. We have done the design, and we are at the critical design that was completed at the end of last year. This is also, don't forget that everything that we have to cool down, we use to avoid fans in order to avoid introduction of vibration. So most of them are cooled down by heat exchanger, by cooling by liquid. And the system, as an entire system, the preliminary design review is now planned for February this year. In order to operate and run all of that one in Chile, close to the Cerro Armazones, here this image is the base camp at Paranal, 25-kilometer distance from Cerro Armazones. And here we have built a technical facility, extremely large building, where we will do the coating, maintenance of all the mirrors. We do here also because we can start all of these pre-coating while the telescope is being built, and therefore gaining a lot of time. And here you see some picture of the inner part of this building. So this is where we have now ready to host all the N1 boxes on the shelves. And this is the part down here for the 5 meters, M2, M3, M5 that will be coated and maintained regularly. So here is the location. This is the entrance to the Paranal Observatory. This is an existing mechanical workshop. This is the BLT for the unit telescope of 8 meters, where we do maintenance of the 8 meters. And therefore, in this area, we have agreed to put the technical facility for the ELT. And in that building, these are the units that will be located. This is the M1 segment coating unit. So this is being integrated in this week, after it has been there for 2 years because the contractor delivered down at the beginning of 2020. Then because of COVID, they couldn't go there for the integration and commissioning. But this is being integrated in these days. And here you see one of the M1 segment that enters here. And then here there is a deposition of the reflective material. For the ELT, it is a silver coating and protected by special material on top of that to avoid the scratching of all of that and so on. There is also a quality control. Here you see the segment, and here there is an optical test bench to check the quality achieved by the reflectivity material. And then there is the M1 washing and stripping. Every time we have to refresh the coating, we have to first remove that one and then put it back again. To give you an idea, when the telescope will be in operation, we will need to do 2 segments recoating per day in order to keep a good reflectivity status of the entire mirror. And this is for the M2 and M3, the 5 meter. Here you see, just to give you an idea of the size, a man. This is where the mirror will be placed and deposited. The reflective material also for them will be silver coating material that will be deposited. To maintain the M4, we will have an optical test tower that will be installed on the top of the Cerro Armazones. There are various handling tools. And in order to avoid, this is one of my dreams, in order to avoid the 2 recoating every day, and therefore a huge operation workload, we are investigating an in-situ cleaning, a brush or other tools we are studying that will fly over the mirror in order to keep the reflective coating at the acceptable stage. Of course, to run all of that one, there are supporting infrastructure that is needed. For example, we have brought the grid, electrical need. We have extended the national Chilean grid to the site, but the electricity supplied by the grid is not always, and I'm sure you have experience, of the quality needed for all the computer and electronic of the telescope. And therefore, we have signed the contract with SAESA, a Chilean company, to install a power conditioning system based on flywheels and generator in order to assure a much higher reliability electricity supply, avoiding power supply interruption, improving power quality, and more. This will have a 5 megawatt full backup generation on site. In parallel, we are also installing a photovoltaic plant in order to supply green energy that will be fed into the grid system. And this will not only supply green energy to the ELT, but also to Paranal and the future CTA telescope. Finally, we are entering into the more scientific world, the instrumentation. No instrument, no science. It is the instruments where we analyze the light collected by the telescope in order to make either imaging or spectroscopy. And so what we do a special follow-up of them. We do a regular follow-up for all the industry contract that I've shown before, but here we are more in a collaborative spirit. So by tradition, ESO is a partner of the consortia, but we also deliver to the instrument consortium detectors and cameras. The roadmap includes 3 first light instruments that I've mentioned before, Mikado, Harmony, and METIS, plus Maori, the adaptive optic module, that are part, all of the 4 of them, of the construction program. But there is also already a program for the future one, and this is part of the Armazones instrumentation program, where Michele Cirasuolo is the program manager, that already include Mosaic and HIRES as a second generation instrument. How does it work? The overall effort, the cost of FTE for the first generation is like the global effort of the domain structure or of the global ELT optomechanics. So we are speaking more or less all of them of a value of around 400 million. Plus, there is about 350 GTO nights, guaranteed time of observation nights, that are given to the various consortia. A quick overview of each of these instruments, 1 slide each of them. Mikado, the principal investigator, the scientist is Rick Davis, close by here, Max Planck Institute here in Garching, Germany. It is a diffraction limiter imager and spectrograph that covers near infrared from 0.8 to 2.45 micron wavelength with a spectral resolving power of around 8,000. The final design review is ongoing. We are at the 3rd out of 4 sessions of them. And you see here the location of that one on the NASMIC platform. You can also identify here the various institutions part of this consortium. Then we have Harmony with the principal investigator Niranjan Tate of University of Oxford in United Kingdom. It is a 3D spectrograph that covers from 0.7 to 2.45 micron wavelength. It has a resolving power that goes from 3,500 to 20,000. It has an image scales from 4 milliarc seconds to 6 milliarc seconds, from the diffraction limit to the seeing limit. The FDR is ongoing. This has been split in 5 sections. The first one started in March last year. And also here you can see all the partners of this consortium. Then we have METIS. The principal investigation is Bernard Brandel in University of Leiden in the Netherlands. It is an imager and IFU spectrograph in the mid-infrared with a spectrum resolving power up to 100,000. The METIS final design review is ongoing, and the final one is planned by the end of this year. Last is the adaptive optics for Mikado, with the principal investigation Paolo Ciliegi of the INAF in Italy. It is a multi-conjugate adaptive optics. The client is Mikado first, but there is also a port for a potential second client in the future. There is the baseline that includes 1 deformable mirrors. We are investigating also for more deformable mirrors inside the instrument itself, plus the M4 that is part of the telescope. It has a wavefront sensing with 3 natural and 6 laser artificial guide stars. There is a delay during the initial phase, but now Maori has went successfully through the preliminary design review and now is rowing towards the final design review. And here you see the partner of this consortium. Second last slide, where we are with the schedule. Today, we are planning for a first scientific light by the end of 2027, with a 6 months planned commissioning of the first scientific instruments before having demonstrated the performance of the telescope by the beginning of 2027. The critical path is today dominated by the domain main structure contract to then go to the AIV, the assembling, integration, and verification phase that is done by ESO. But we are very tight both with the M4 and M5. M4 for all the completion of the reference body. Silicon carbide is today our headache, both for the reference body of the M4, but also for the construction of the M5 mirror That is one of the most critical technology situation that we have in the telescope. Last slide, just to give you an idea of how does it look like today, the site. Here you see the outside growing of the foundation for the dome. There is good progress. This picture was taken before my visit that I've shown before. Today we have already started the pouring of the concrete in the central part of the foundation for the main structure. What you have here, this would be the entrance to the telescope, to the dome. This is the pit where the M4 tower will be installed to do maintenance, but also integration of the M4. And this is where the instrument will also pre-assembled before going on the telescope. Today there are, as I said, 140 people on site for a capacity of 500, but because of COVID, we are limited. So this is really a great endeavor, a great project. We are fighting against all the difficulties, but we really look forward to have this highway towards increased knowledge ready for all of the scientific community of this world. I thank you very much for your attention.
Thank you so much for a great talk on a stupendous project. So I had one preliminary question. What is the involvement of US teams in this project, if any?
Participation of United States?
Yes, if any.
We do have, you know that one of our, I don't want to call it competitor, but let's say a friend of similar size is the 30-meter telescope, but also the Giant Magellan Telescope. We have an excellent relation in terms of identifying scientific goal, but also in terms of technologies that we share. But there is no active participation in the project today from United States. So today, United States has their program that is composed, as I said before, by the 30-meter telescope and by the Giant Magellan Telescope, but they are not part of the ESO's ELT today.
And one related question before we go to Dick Garwin and John Grunsfeld. How are the, I think you said that part of the time is allocated to the partners and some of the time is allocated to others. How will US astronomers get access to time on this telescope?
Okay, that is, there are two set. The nights of observation, there are some of them that are guaranteed to the partner of the consortium of the instruments. And there is a limit that has been given by our council. We say, okay, 10%, 15% maximum can be given as a compensation of the effort to the instrument consortium. All the rest is open to the entire world scientific community that has a process to apply to give their ideas and say, look, this is my idea, my program. Can you please use your telescope with that specific instrument to give me the data? And they submit this request to the ESO community. The ESO will go through all of them. They will scrutinize, they will classify, and then they say, yes. And this is independent if you are part of one of the ESO member states or not. There are obviously some other rules, but anybody can apply with their justification, with their program, to the observing time of the ESO's telescope. ELT will be one of them.
And let's go to Dick Garwin. Dick, do you want to ask your question using your microphone, or do you want me to read the text? Dick is a physicist that you probably have heard of.
My congratulations to the ELT team for stupendous progress. It's really an awe-inspiring project. But around slide 59, what exactly is being brazed? You have these segmented mirrors and they're made into one by being brazed together somehow.
You said slide?
About 59, I think it refers to brazing.
Is this the slide? Yes. Okay. We are speaking about probably the most complex mirror, M5, the last one before the light is directed to the instrument. The mirror here is composed by 6 petals. Each 6 petals has to enter within a specific weight, size, dimension, and all the rest. The mirror M5, let me go back here we are, is composed by 6 petals that have to be brazed together in order to give this shape. Before brazing together, we have to deposit a 900 micron thickness of a carbon vapor deposition of silicon carbide on top of them. So we first do the CVD on each of them independently. We have to verify if this layer is well bonded, is adhering properly, because this has been one of the first difficulty to have such a thick CVD coating on top of each of them. Then we have to braze together, taking care of this 900 micron thickness that has to combine with the others. We have to do for the 6 of them, and then we start the grinding of the entire mirror together. And all this process is pretty difficult, has never been done, so we are pushing forward the technology in this field. It has been done in the past. The big mirror of Herschel, for example, did not have the CVD. It was already a silicon carbide mirror, but not with the CVD deposition of that. It has never been done such a big with a CVD coating on top of that. So this is one of our top technical risk of the telescope. But we are already validated the CVD deposition and also the removal of that, because often we have to repeat it if it is not successful without manufacturing again the full petal. We do have also petals, spare petals, some of them with, some of them without the CVD coating on them. Then we have to go through the brazing, and then we will have to go to the pre-polishing and polishing. Does this answer your question?
Yes, thank you.
Thank you. You can stop screen sharing. We'll go to John Grunsfeld, who you may know is the astronaut who was chiefly responsible for repairing the Hubble and correcting its optics. So John, you can go ahead and turn on your mic. And
all right, thank you, Larry. Roberto, thank you very much for the wonderful talk. I have a very small comment and then a question. The small comment is that the picture of the coast of Chile was taken from Space Shuttle Discovery with Hubble in the background. So, and it's a wonderful view. With a salute to Riccardo Giacconi, how do you keep all of the systems engineering? And so, for instance, how do you keep all of the tolerance buildup from item to item so that the light that enters the telescope actually can achieve the science at the instrument?
We do have a model that is continuously a model that of the entire system. Okay, we do have a validation models that at the beginning it was a simulation with all the requirements and the related tolerance implemented. That now we are obviously following it up very closely with the as-built performances that are qualified, validated, and confirmed, and we continue running these validation models in order to keep often, for example, the validation model is the basis of accepting a change request. When a contractor comes to a change request that is impacting one of the requirements, we run this simulation model in order to verify if the new data that the contractor is giving us in terms of performance, for example, of the position actuator stroke, or of the flatness of a mirror, or of the flatness of the reference body, if that will still return the final performance requested by the entire system. So this is one of the several tools that we are using in order to keep the system engineering under control. We also have linked all the requirements together. So all the requirements of all our contracts are linked together in doors. You might be familiar with this tool. And therefore also there, this is a tool that we have to question or to introduce the change, verify what are any other requirements that are affected by that change specific requirement, to verify if the final result is affected or not. So we do have a very heavy, a very well-structured system engineering that is my foundation of the program in order to confer if the performances or the changes that are requested by the various contractors are affecting the final performance of the telescope or not. Does this answer your question?
Yes, thank you very much.
Welcome.
Are there any aspects of that particular set of computational tools that you're implementing artificial intelligence programs on?
No, I'm not implementing any artificial intelligence. This is done by real engineers so far, by my colleagues.
AI doesn't quite qualify as yet. I just wondered. Let's have a question from Frederica Derema, who formerly was the head of the Air Force Research Laboratories. Frederica, you have a question?
Yes, well, first of all, thank you for the great presentation of a very great project. One very simple question. You talked about the using solar arrays for the 5 megawatts of power that you need. Why not wind energy? I mean, you can put a lot of windmills up there. Or is that creating some disturbance?
Okay, thank you for your question. We have done, together with the Minister of Energy in Chile, a 2-year campaign in exploring on-site what would have been the best renewable energy, green energy. So the Minister of Energy installed the tower with all the anemometer, with all of that one. And the final result was, first of all, that area is the one with the highest radiation in the world. We are speaking about 1,200 watt per square meter first. And then it is certainly a passive system and therefore reduction of maintenance apart from some dust, but also they are implementing a way in order to avoid the position of dust on the panels. For what concerns the windmill, this indeed introduced some disturbances in terms of the wind effect behind the downstream the mill that is pretty long. We are speaking about several diameters of the turbine downwinds, and this will certainly affect the quality of the image that the telescope will observe. So at the end, and also for the quality of the sky that we have there, also for the constant, I mean, you could have days where there is very low wind and very low production. At the end, taking all of these situation into account, the solar panel has been chosen as the best.
Thank you. Can I ask another question?
Okay.
Last the last lecture and one a few months ago, we heard a talk from Olivier Guillaume, and he talked about adaptive optics. And he, their, in a sense, methods looked pretty cool and advanced. Has anybody of the projects that are developing the instruments adopted any of these methods by them?
Okay, I do not have those details. I don't know if Michele, my colleague, is more aware of this one. I am personally not in those aspects. Yeah. Michele, can you help?
Sorry, can you repeat the question, please? I missed it.
Yeah, let me translate a little bit. So I think the talk that Olivier gave on earlier in January was on extreme adaptive optics. And these are being implemented on the Subaru telescope.
Yep, the XAO,
so,
yes.
The question is, are those being talked about or implemented on the ELT?
So yes, but as a second phase for us, in the sense of at the moment, we are starting with single conjugate and multi-conjugate adaptive optics, because to do the extreme adaptive optics, we need to really understand how the system works to correct all the vibrations and stuff. Mm-hmm. So our third generation instrument is called PCS, planetary camera spectrograph, that will employ an XAO, an extreme adaptive optic system, a double stage AO. So all these AO community are all talking together. So all the AO groups are really connected. We have 2 or 3 meetings per year where all the people get together. They really try to understand what is the best way to analyze the data, correct the wavefront sensor, techniques that you can employ, including artificial intelligence. In this case, for extreme adaptive optics, people are looking at AI to use those corrections to improve the performance of the adaptive optics. So yes, not at the beginning, but we'll do extreme AO later on for the ELT.
Thank you.
Thank you for that question. We have another question from PSW member and GC committee member Connor Nixon, who is out at Goddard. Connor, can you turn your mic on and ask a question? Or should I read it out?
Yes, yes, thank you. Great talk. Very impressive project, and I'm looking forward to putting in some applications to use this wonderful telescope in the end of the decade. But I know that there's always some long-range planning, which goes into organizations such as ESO, and I'm wondering if there's any thinking of what telescope could come after ELT. Is there any thinking of that level yet?
Okay, I'll give you my engineering feeling. I doubt that there will be bigger telescope continuing growing in that for several reasons. Because we are really today, as far as I can judge, at the limit of the construction, even if the first idea of the ESO extremely large telescope was a 100-meter size. So that was called OWL, overwhelmingly large telescope. That was the beginning. Yeah. It was 100-meter size, but then it was not discarded because of confirmed impossibility to build it, but because of the high risk for the secondary. The secondary up there that you've seen, we have it on 4 meters. That would have been more than 6 meter size. And the risk of having it up there was considered too high, putting everything at risk. To go back to your question, I doubt that there will be a big one. Probably they will start thinking of a bigger interferometer, maybe even putting a telescope in the space, performing interferometer measurements. But in that, we then go into the scientific world. And I don't know if Michele wants to comment, but today, what I heard are a big spectroscopy telescope, a big survey telescope, but not increasing the size of the visible near infrared telescope as the ESO ELT or the 30-meter telescope or the GMT.
Let me confirm what Roberto said. The one possibility could be, and people start looking into this, to get spectroscopic telescope of the order of 15 meter in diameter, 12, 15 meter in diameter, but with the very large field of view, 5 to 10 square degrees, and highly multiplexed, 20,000 objects simultaneously. So that it's because you have LSST, which providing a huge amount of data in terms of imaging, and you have to get spectroscopic follow-up of this. There's Gaia, there is LSST, there is all the space mission like Euclid, WFIR. So you have a lot of imaging, and you need to get massive spectroscopic follow-up for this. And you need to get a 12 to 15 meter diameter telescope with a lot of spectroscopic capability on top of it. That is one possibility post ELT.
Thank you.
Have a question from the web, which I'll sort of modify. And what's the reason for choosing what you've chosen as a reflective surface? In particular, he wants to know for using silver instead of aluminum. And this is from Eric.
Yeah, the reason is because it is providing a wider coverage answering to the scientific requirement. So with silver, we are covering larger bandwidth of the wavelength with respect to the aluminum. But just to be precise and to answer the web, all the mirrors will be silver protected coating, but M4 will be coated with aluminum to take into account the thickness and the difficulty of that mirror.
Thank you. A question from Wendy Friedman, an astronomer. I think she's University of Chicago. Wendy, could you please ask the question or indicate somehow that? Good.
I love this discussion of future telescopes, and even before we finish the current generation, maybe we'll one day have an EELT in space. I did want to congratulate you on this terrific progress. It's just really wonderful to hear. And I was just curious to hear from you what you think are the major challenges that are remaining in construction of the EELT.
Thank you. Thank you for your question. Okay. I could open my risk register, but I don't want to do that. The major challenges, as I mentioned before, it is certainly M5 in terms of technology. We need to reach, this is the first one, we need to complete the flatness of the reference body. You have seen, maybe it was not clear, the reference body is a 3-meter silicon carbide, plenty of holes, because there will be all the actuators for the adaptive optics mirror of M4. And therefore, this shape is pretty difficult to flatten, to measure, because you cannot easily do as you would do with any other mirror, plenty of holes here and there. And therefore, it is difficult to have this flatness at 5 micron root to valley flatness. That will be the reference of the M4, and therefore the reference for the moving of the adaptive optic mirror. So we go M5, M4 for this reason. Obviously, managing of the contracts, a big contract such as the dome and main structure in Chile in a pandemic, this is a pretty high risk. And then something that you might consider it's a day-to-day activity, but at the end, because we have to move several items from Europe to Chile, it is the handling of the optics, transportation of those big mirrors from Europe to the mountain. You cannot imagine, I have passed in the past experience, that is pretty a risk. It's a day-to-day, you can consider it easy, but nevertheless, it is that. And then, of course, the commissioning, putting all of that together. It is certainly, it's a prototype. It's not even a Formula One. I used to call it a Formula Zero because it has never been manufactured and built and commissioned such a gigantic and precision system. And therefore, putting all of that together, even if we are doing in-house emulation, test benches with all the control system and all of that one, okay, we are considering what will be the final as-built performances, but when we will put all of that together in place will be the first time, and we will have to make it working, will certainly be a fascinating. I can imagine we will always be there in order to see what are the performances and all of that. So this sharing with you how I see the biggest risk and the difficulties in front of us, but we are rowing and day and night all together to have it soon in on sky.
Great, thank you.
I have a related question I'm going to sneak in here. How did you, this project is stupendous in its scale, and it seems to have a very high level of complexity risk, let's say. You're doing a lot of things, as you say, you've never done before. How did you navigate getting it funded?
Okay. First of all, to have it funded, we had demonstrated many of the risks were prototyped, okay, in scale or some of them. So we could never build all of that together. We have certainly demonstrated, and it went through several commissions, analyzed in the performance in what was the construction proposal that have been gone through reviews for their approval. So that is how we had it funded. At the beginning, it was funded in a stage. Now all the stages are funded. So we do have in the ESO bank account the funding for all of that one. We are speaking about the first generation instruments. Now we are also looking for the second generation, the one that Michele was mentioning before. But we have demonstrated that we can make it. And I really hope that that will be demonstrated pretty soon.
We have a question from Eliad Perez, or Peretz. Eliad, do you want to ask your question?
Yes, can you hear me?
Yes.
Hi, first of all, thank you. Great talk, and it's really inspiring to see the progress. In one of the science cases you showed with us, you mentioned that you think you would be able to explore Earth twins, and I'm using an exact wording. Can you please expand on how this could be achieved and how all the contrast challenges here could be met? As we all know, Earth twin requires 10 to the minus 10 contrast.
So the question is that you had said in one of your slides that you would be able to resolve an Earth twin, and he is asking how you achieve the contrast ratio that's necessary for that, which is about 10 to the minus 10, according to the questioner.
Yeah, I'll take this one. Hi, Elliot. Yeah, so this is our long-standing problem of having this high contrast to perform extremely well. You know, we've been working on that together on these things. So the idea is is to use the third generation instrument, these extreme adaptive optics, to push the Strel ratio to the 95 to 99%. That already start helping the contrast work a bit more on the choreographic aspects. And then, as we know, star shades is something like we would like to have to really achieve the 10 to minus 10. What people are telling us that from the ground, you can reach maybe 10 to minus 8 in contrast with extreme adaptive optics, because you really shrunk the PSF as much as you can, and you get this 99%, 98% Strel ratio. But to get 10 to minus 10 is really challenging. from the ground because all the speckles and all the problems you're going to get. So.
Thank you, Michel. And again, inspiring. I've been following you for the last few years, and I'm just amazed by what you guys achieved. So congratulations.
And we can do more together, I'm sure, Elliot, right?
Yes.
We have a question from another astronomer, Carrie Liss. Carrie, want to ask your question?
Well, first, I'd like to say, as somebody who's worked and actually visited ESO and Garching and taken observations La Silla, it's wonderful to see how ESO is staying on the cutting edge of research. I used the 3.6 meter before HARPS took it over to look at comets. So thank you for tonight's talk. It was fantastic. I have a small quibble. The picture you showed us of an imaged exoplanet is actually from Beta Pic. It wasn't, Proxima B has never been imaged. It was actually seen by radial velocity measurements, looking at the star moving around.
Yeah,
but
correct.
still, it's a fantastic result. It's a fantastic ESO result. So I'm just quibbling.
That is a sphere, yeah, correct. It's a sphere image of Beta Pic, is not Proxima Centauri, yeah.
And I have a small question is, we all know COVID has set the world back a number of months to years all over. How much has that affected this fantastic project? And it's a very ambitious project, would you say? How much time have you lost?
Like it was a year.
Not sure.
How much time we lost, Roberto? How much time we lost due to COVID?
Okay, I can tell you that the site was construction site in Chile was effectively closed from June 2020 to May 2021. But you need to add 1 month before, because it took more than 1 month, let's say 1 month, to effectively close. What I mean is since you decide to close the site, you need minimum 1 month to send everybody home, to put it in safe condition, to bring all the machining home, and so on. So let's say from April 2020. Reopened in May 2021, but I'm sure you understand that when you decide to reopen, then you need to find again more than 20 subcontractors to go on site, to arrange all of that, and so on. In short, if you ask me today how much time we have lost, we are very close to more than 1.5 years. But as you well know, we are not yet there because of the long lead time of several electronic components, extremely longer time of raw material, the transportation. I'm sure you have seen how it has increased in terms of availability of the transport container. The cost has increased. So today, if you ask me like that, we are more around 1.5 years net, but it could be more.
Oh my. So congratulations on keeping on and sticking to getting to be done by 2027. Are you doing most of your staging out of La Serena? I remember that's where I flew up from Santiago in order to go to La Silla, do you have a closer city that you're working from? Just curious how you do your operations.
We stay mostly in, so this is Paranal, it's closer to Antofagasta. So okay. we fly up to Antofagasta, and then the closest route is from Antofagasta up to 2.5 hours. It's very, very close to Paranal. So practically is from Paranal, you go down the valley where the road is, you go on the other side of the mountain. So it's 25 kilometers from Paranal.
Today, we have recently started board and lodging at the foot of Armazones, but because of the technical facility that I've shown is sitting at Paranal, we are part of the same observatory. So Armazones will be seen as an additional telescope, part of Paranal Observatory. So we can board and lodge at Paranal Residencia. And as Michele was saying.
Thank you for informing me. One other small question. I remember learning at one point that La Silla, at least, was international territory. I believe by treaty, it was actually European as well as Chilean. Is the same for Amazones and Paranal?
Absolutely, yes. It is a sort of diplomatic land, because ESO is recognized as an intergovernmental organization by the Chilean authority, the Chilean government, that has given to us the use of that land special for scientific purposes. And Armazones, it has been extended, the area that was given for Paranal. Now it has been extended to include also Armazones. Is a pretty large area in order to avoid also mining activity that could deteriorate the quality of the seeing. And it is exactly the same as the one that you remember is at La Silla.
Very good. Thank you very much.
We'll take a question from the web, and then we'll go to PSW member and NIH Professor Emeritus Carl Merrill. So from the web, we have a question from Maria Francesca. She asks about how exoplanets will be detected. And specifically, she says, will direct imaging be the only method that the ELT was used to infer the presence of exoplanets around other stars, or are other methods going to be employed? So
we're going to use
go ahead. Sorry.
We're going to use both. We're going to do both direct imaging, but also radial velocity measurements, both in. So the power of the ELT is not much on discovering exoplanet. It's more trying to characterize exoplanets. So we're going to build up on all the discoveries of Cheops, TESS. But the idea with ELT is because of the collecting power. And for example, we have a new instrument coming, is called Andes, which will do 100,000 resolution in spectroscopy across optical and near infrared. What you can do is really try to start getting into the atmosphere characterization of the planet. So you really start getting, you feel the power of the ELT in these small absorptions for which you need the power of the collecting of the ELT. But all the first generation instruments are provided with a chronographic capability, high contrast. It's not high, it's 10 to the minus 4, 10 to the minus 5, but both in imaging and in spectroscopy, Mikado and Harmony, they will have a high contrast image, high contrast to the level of 10 to the minus 5 capabilities for exoplanet. And METIS, which is the mid-infrared instrument, that it's almost fully dedicated to exoplanet science, and we have different type of chronographic, apodizer, vortex, and again both in spectroscopy, in imaging, and also in IFU with chronograph. So all the instruments are equipped to do different type of exoplanet characterization and study.
I'm going to do one last question, and I want everybody to appreciate that it's 4 a.m. in the morning for these two generous speakers, and I really appreciate that they're willing to stay up that late for us. Our last question will come from PSW member and molecular biologist Carl Merrill.
My main question is, how does this telescope image individual stars or objects for spectral analysis? I remember some of the other telescopes I've seen use fiber optics to look at each individual star and analyze the spectra. But I presume you have more sophisticated methods for this. And the other part of that is, can you also measure polarization of the light?
Should I take Roberto? So what we do in imaging, Mikado, we do imaging of individual stars over a field of view of 1 arc minute, fully corrected by AO. That means working at the diffraction limit of the telescope, which is 10 milliarc second. So there you can really start resolving individual stars, even in crowded field, much, much better than any of the previous telescopes before. And in spectroscopy, we have both integral field spectrograph, like Harmony, where the field of view goes up to 7 arc second. And again, at the diffraction limit, there you get an IFU type of spectroscopy. So you get every single spaxels get the spectrum. So that is very good for crowded regions and internal region of the galaxy. And then we have a multi-object spectrograph, and that is a fiber-fed multi-object spectrograph. So we're using both the IFU slicers and multi-fiber spectroscopy for this. And on top of that, we have single object spectroscopy in slit, traditional slit spectroscopy, both in Mikado and, and in METIS. So we are employing a bit of everything somehow, but nothing completely new or super fancy like micro shutters or stuff like that. So we have fibers, slit, and IFUs.
Thank you.
Well, thank you, Roberto, for giving this talk, and Michaela for joining with us, sharing your time with PSW and giving us an overview of the ELT. You are free now to get some sleep.
My pleasure.
And again, thank you both very much. We really appreciate it. It was a fabulous talk. It's an amazing project. And I think we're all going to be really, really excited to see images when you're done in a few years.
I thank you and the PSW Science Foundation for giving us the opportunity of sharing with you the status of the ESO ELT. Thank you again.
Thank you.
Have a good evening.
Thank you. Good evening.
Bye.
Bye.
So this ends PSW's lecture series on the 3 very large visible light infrared telescope projects currently underway, in addition to the video recording of tonight's lecture on the ESO ELT. You can watch videos of the PSW lectures on both the other projects, the GMT and the TMT, and the 2 PSW lectures on adaptive optics on the PSW website and the PSW YouTube and Vimeo channels, where you will also find over 160 recordings of lectures on interesting topics like this of science, technology, history, and biography. Before you go, a few important notes. The spring schedule is still being formed. We're a little late on that, but these are the dates, most of the dates. The next meeting, which we hope will be in person, but ultimately that will be determined based on COVID and COVID-related measures in place at the time, will be on February 25th, and the speaker is yet to be announced. The 2,455th meeting on March 11th will the lecture will be by Melissa Harkins of the Smithsonian Institution National Museum of Natural History, and she'll be talking about exploring biogeography and evolution with ancient and modern DNA. She works on interesting squirrels and lemurs and other animals like that. And on the lecture number 2,456 on March 25th, we will be having a lecture by Kim Prather of the Scripps Institute of Oceanography and the University of California, San Diego. And she'll be talking about aerosols, ocean spray aerosols, aerosols we've all been reading about in the newspaper, and how aerosols spread chemicals and other substances, including viruses. Kim and Rami Amaro are collaborators, and so Rami may join in on that talk. And the other lectures are listed here by lecture number and date, and you might want to write the dates down. Speakers will and topics will be posted in due course. Let's have a thank you to tonight's Zoom crew. Robin Taylor does all things AV and Zoom, who you can't see. She's in the background and serves as PSW corresponding secretary. James Heelan, our recording secretary, who did a fabulous job with the minutes of Olivier Goyan's lecture on extreme adaptive optics. And Anne McQueen, who should be on this list but isn't, who is our social media director and takes care of the questions from the web. So please join me in thanking them. And with that, I will now adjourn the 2,453rd meeting of the Society. I wish everyone a good morning, a good afternoon, a good evening, or a good night, wherever you may be. Please join us for our next lecture. The meeting is adjourned.